So now let's start the chapter of coloring. And what is coloring? So in undergraduate graph theory, we learned that the coloring means that if we have a graph, then say vertex coloring means that we want to color the vertices so that the no two adjacent one have the same color. So in other words, if you collect all the vertices with the same color, then they form independent set. There are no edges between. We can a bit generalize this notion. So let's say P be a family of graphs. And we say P coloring of G is a coloring of vertices such that each color class induces a graph in this P. So traditional coloring is we take this P as a collection of empty graphs, collection of graphs with no edges. So collection of independent sets as a graph, then we get this. And we say P chromatic number chi P of G is the minimum K such that G has a P coloring using K colors. So with this definition, this family P could be arbitrary family. But for those arbitrary family, this coloring or chromatic numbers are not so interesting. So there are some, at least we need to get some properties of them so that they are not totally unpredictable. So it becomes somewhat interesting. So there are some classes of the graph, some families of the graph that we are considering. So we say that this P is closed under, say, taking subgraphs. So we call those as a monotone family of graphs or monotone class of graphs. Then we have this inequality for H subgraph of G. Meaning that if we have G, and then we have a subgraph H, then if G can be partitioned into several classes so that each color class induces a graph in P, then for H, which is a subgraph of G, it may have a smaller number of vertices and smaller number of edges. Then this partition induces the same partition, induces a subpartition in H. So let's say this is x1, x2, x3, x4. Then for H, we take the y1, which is x is in H and x is in xi, y1, x1. This is in VH, means that the x is indeed in VG. So we can partition, make this partition. And that gives us the partition. And in here, now each of h, x, I, the graph that h induces on this vertex set is a subgraph of, subgraph of G induced by this xi. And then we know that this is in P. Then we also know that this is in P. So any coloring, P coloring of G induces a P coloring of H in natural way. So we get this inequality. And also if this P is closed under taking disjoint union, which we sometimes call additive property or additive family of graphs, and in addition also monotone, then we can just reduce the problem of finding P chromatic number into a connected component. This is actually maximum among all its component. Let's define some interesting graph classes. Let's say O sub R be the collection of all graphs with components, such that, let's say, all graphs such that all of its component have order and most say R plus 1. And S sub R with the collection of graphs with maximum degree and most R. And DR be the collection of R degenerate graph. Remember, R degenerate graph means that if you have R degenerate graph, then any subgraph of it has a vertex whose degree is at most R. Equivalent formulation is that you can order the vertices so that every vertex has at most R previous neighbor. It could have many neighbors later, but it has at most R neighbors on the left. And let's say CR with a collection of graphs, say H with its edge connectivity at most R. Say, no, let's write it this way. Graph G, as I was written before, it is not monotone because you can consider this graph. This graph has connectivity 0, so we give the connectivity 0 for this connected graph. But this has connectivity higher. So it's a collection of graph G such that every subgraph of this has a smaller connectivity at most K. Again, this is R, sorry. So these namings are not standard. Lots of cases they give different name for the such coloring. For example, OR coloring, OR chromatic numbers are called clustered coloring. And then SR coloring is called defective coloring or improper coloring. And so those names are, these notations are not really standard notation, but let's use this too. In this course, let's use this. So one thing we can see is that for say this P is in this OSDC, we know that PR is a smaller class than PR plus 1. So once you increase this R, you get a more and more graph. And once you have a more and more graph, then it's easier to actually color the vertices. So before you take a coloring, you take this color class. And then here, this has a maximum degree 3. So this is not S2 coloring. But once you increase, then now this was not in S2 before, but now in S3. So this becomes S3 coloring. So before S2 coloring requires more than 4 color, but now 4 color might be suffice. So this shows that, this containment of the graph family implies that we have PR is, chromatic number is bigger for, and once you increase R, it gets smaller for each this P. And also, you can see that OR and SR, TR, and CR satisfy this containment. If every component has size m mod R plus 1, then it's, the vertex there has m mod R neighbor, so this relation holds. And if maximum degree is m mod R plus 1, then any ordering gives the degeneracy ordering, so this is R degenerate. And then if it is R degenerate, then every subgraph has a vertex of degree m mod R, so its edge connectivity is m mod R. So this shows that in terms of coloring, we get this inequality. So, and moreover, if R is 0, then this P0 is same as just chromatic number. Because when R is 0, then this just means that all the component has size 1. So it's same as, each color class must be independent set. And that applies to all other. So now what we will do is we will find some bounds on each of these coloring. And in undergraduate graph theory, we learned several techniques to prove some bounds on chromatic number. And some of the method extends to, some of these colorings. So today let's deal with some simple one. So one of the way that we proved the most simple bound on the chromatic number was that the chromatic number is m mod delta plus 1, maximum degree plus 1. And how did we prove that? We proved that we just order the vertices so that we color one by one in greedy way. And once we have to color this vertex, we see how many neighbors, we see the colorings of the neighbor, and then we use the coloring which is not used before. So we can actually slightly generalize this greedy coloring to, let's say, the R greedy coloring with respect to vertex ordering P1 to Pn. It assigns to each vertex vi in order. The least indexed color that has not been used on fewer than that has been used on fewer than our earlier label. What it means is that you color the vertices, and you have, say, some red vertices and blue vertices. And then let's say R is 2, and at this time you have neighbor, 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 neighbor. And also, say, red color is 1 and blue color is 2. Now you color one by one. When you color this, you see its earlier neighbor, and then you found the color. Let's say there are infinitely many colors with the ordering. You check whether each of the color is used smaller than R times on each neighbor. So red is used 3 times, so red is out. But blue is used only 1 time. 1 is smaller than 2. So we give the blue color. And then next one, if it has neighbor, 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 then red is used twice and blue is used twice. So you give the new color 3. And so on. So you give the color on here, which is among the colors which has used less than R times on the earlier neighbors. You choose the smallest color. Then if you use one greedy coloring, then you immediately get this upper bound. Then what happens if you use R greedy coloring? Then you can show that this D sub R minus 1 coloring satisfy this. So in other words, so what's this? We know that maximum of H of G, maximum of delta of H for all subgraph of H is, say, K. That means G is K degenerate. So degeneracy of G is K. So this is same as K plus 1 over R when K is the degeneracy, and take the Schilling. Anyway, so for this degeneracy coloring, so D sub R minus 1 coloring, we have this. We can actually prove. Let's say T is this number. And we consider smallest last ordering P1 to Vn. So this is the ordering that you have a graph. You take a vertex with minimum degree and you put on Vn, and you take a remaining graph, and then there you take a vertex with minimum degree and you put it n-1 and so on. So every time you take a V1 to Vi, then in this graph, Vi is one of the vertex with the minimum degree. And we apply R greedy coloring. Then what do we know? Since this Vj has the minimum degree in the graph which is induced by B1 to Bj, and we know that, let's say this graph is Gj, then we know its minimum degree is from this is at most tr minus 1. So Bj has at most tr minus 1 earlier neighbor, at the moment of coloring this vertex. Then by pigeonhole, this has fewer than r earlier neighbors in some color among the first T colors. So we give Bj such a color. And this will complete the coloring. And then now we have to show that after this completion of coloring, this is actually a desired, d sub r minus 1 coloring. Then for any subgraph H whose vertices have the same color, with this above, ordering induces natural ordering in the vertices of the H. The vertex of H appearing at the last in the ordering has at most r minus 1 neighbors in H with the same color. So each color class induces an r minus 1 degenerate graph. So this finishes the proof. So this, argument for this, finding the upper bound delta plus 1, this greedy algorithm actually generalized to this degeneracy coloring, D sub R coloring. So today we finish here, and then next time we learn more about the other colorings.